Hi, my name's Etienne Van Wyk. Here's my ZID, Z55591051. So starting from question 9, we have the planet and moon scenario. The planet moves in a small circle, and the center of mass in question 1 was for the orbit of the sun, and the planet was very close to the sun. For question 4, changing the planet's mass did not noticeably affect the mass location due to the center of mass location due to the planet still being much less massive than the sun. And for question 7, when the sun's mass was reduced to half, the center of mass shifted slightly away from the sun's center, but it was still within the sun due to large mass difference. For C, in a planet-moon system, the center of mass, called the barycenter, is relatively close to the moon, and closer than in the star-planet system because the mass difference is much smaller than between a star and a planet. This can often mean the barycenter lies outside the planet's surface, causing both the planet and the moon to orbit around the shared point in an orbit that looks like a wobble for the planet. Now for question 11, this radius here is around 0.49 astronomical units. I picked 4 orbital distances. One is 0.2 AU, one is 0.6 AU, one is 2.1 AU, one is 0.985 AU. Here I made the table, and the system follows Kepler's third law because the ratio of period squared to radius cubed is around the same number, which you can see here. The values of period squared to radius cubed are relatively consistent, so the orbits follow Kepler's third law. The slight variation is due to human error when I tried to make the orbits circular. So, for 15, Mercury will have the fastest orbit, 47.9 kilometers per second, because it's the closest to the Sun. Due to this formula, velocity squared is inversely proportional to the radius of the orbit. So a smaller orbit will have larger orbital velocity. And for that reason, Neptune will be the slowest orbital velocity. What's the reason? Well, it's Kepler's third law and Newton's law of gravitation. The weaker the gravitational pull means the planet moves more slowly in its orbit when it's further away. And for Neptune, it's very far away, and for Mercury, it's very close. Now, what did I learn from this experiment? In this experiment, I learned about Kepler's laws that explain how planets orbit around the Sun. I learned to apply these laws and find orbital velocities and periods to understand the motion of the bodies in space. The experiment extended my understanding of astronomical theories that explain planetary motion and what astronomers can use these laws for in relation to the solar system and beyond. In the process of editing the video, I'll be optimizing and researching. First, I'm filming a video and screen recording the content. I'll edit the audio, and I'll try to present in an organized way. I've overlaid my Word document of answers, and I will try to meet the rubric guidelines. Now lastly, Kepler's laws. They were written by Johannes Kepler in 1619. The laws describe planetary motion. He accurately predicted properties of planetary orbits in the solar system and the entire universe. For the first law, planets move in elliptical orbits, with the Sun at one of 2 focus points. And more accurately, the orbit of a planet is an ellipse, with the Sun at one of 2 foci. You can see in this diagram. For the second law, a planet sweeps out equal areas in equal times. This means a planet moves faster when it's closer to the star and slower when it's further away. A line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time, as you can see in this diagram. Now, finally, the third law. The square of the planet's orbital period is proportional to the cube of its average distance from the Sun. The time it takes to complete one orbit around the Sun is the period, which is directly proportional to the cube of, the square of the period is proportional to the cube of the radius, as you can see. And here's a diagram. More accurately, the square of a planet's orbital period is proportional to the cube of the length of the semi-major axis of its orbit. And here's a diagram. And that's it. Thank you.